Hello viewers, welcome to our YouTube channel Incredible Maths. In this video, we will see content related to the examples of group and continue with the properties of group. So already in the previous two videos, we saw the definition of group and some examples of group and some examples for not a group. So now we will see whether this verify whether R power n is a group under addition. So what is R power n? R power n is a set of all n tuples such that each entry is a real number, is x1, x2, xn, such that xi belongs to R 1 less than or equal to I less than or equal to n. Suppose if we take any two elements, so x is equal to x1, x2, etc. xn, and y will be on the form y1, y2, yn. Now we define the addition x plus y as x1 plus y1, x2 plus y2, etc. xn plus yn. So based on this operation, so we can prove that R power n is a group. Suppose if we take xy and if we add this x plus y will be of this form. So here each x1 plus y1 may be some z1, z2, etc. z3, where all these zi's belongs to R. That is, each compound is a real number. Therefore, addition is closed. So this implies R power n under the operation addition is closed. So this is first one. So second property is associative. So here we can take x plus y plus w equal to some x plus y plus w. So this will be associative. So this can easily be checked. So take x is equal to x1, x2, xn, and y is equal to y1, y2, yn, and w is equal to similarly w1, w2, wn. So if we add, compute the left hand side and compute the right hand side, both sides will be equal. So therefore associative is true. Now identity. So we can take the zero element or identity element as E is equal to the n tuples with all integers 0. So this will be the identity element. That is, we add x1, x2, xn plus 0, 0, 0. So this will be equal to x1, x2, xn. So this is the identity element. Next we will compute inverse of x. So x1, x2, xn plus some other element y1, y2, yn equal to 0, 0, 0. Then this implies x1 plus y1, x2 plus y2, etc. xn plus yn. So this will be equal to 0, 0, 0. So equating the each components, each component of left hand side with the right hand side. So x1 plus y1 is equal to 0. So this implies y1 equal to minus x1 and so y2 equal to minus x2 etc. yn equal to minus xn. Therefore, what is inverse of x? So inverse of x is y. So what is y? So y is equal to minus x1 minus x2 minus xn. So this is nothing but x1 x2 xn, that is y is equal to minus x. So the inverse of x is minus x. So all the four properties are satisfied. Therefore, the set R power n under the operation addition is a group. Now there are some more examples. So you can construct your own examples also. So set of all continuous real valued functions defined on the closed interval a comma b is a group under addition. So this you can check or verify. So next we will see a definition of subgroup. So definition of subgroup. So given that G is a group, let G be a group and this capital H be a subset of G. Now this H is a subgroup of G if H itself a group under the same operation of G. So let us repeat. Let G be a group and H be a subset of G. H is a subgroup of G if H itself a group under the same operation of G. So given that H be a subgroup, okay, so therefore G is associated with some binary operation star. So now we take a H a subset of G. Now H is a subgroup of G if H itself a group under the same operation of G. That is, here H comma star should be a subgroup. H comma star is be a subgroup. So now let us see an example. Let's take an example. Example Q comma plus is a group under what operation? Addition. Now take a subset is a subset of Q is a, so this is subgroup. It's a subgroup of G, the subgroup of Q under plus. So we can take some other example. R comma plus is a group, whereas Q subset of R is a subgroup of R under addition. So similarly, you can take a C comma plus set of complex numbers is a group or subset of C is a subgroup of C under addition. Now let us see subgroups under the operation multiplication. Under the operation multiplication. So far we have seen the subgroups are the groups with operation addition, and okay, so here we have seen, suppose if our star operation star is multiplication, then the properties for every a comma b in G, so we should have a dot b and associative a dot b dot c equal to a dot b dot c, and identity element will be e equal to 1, and inverse of a will be 1 by a. So now examples of groups under dot, that is multiplication. So r comma dot is not a group. Why? Because so 0 will be in R and inverse of 0 will be 1 by 0. It's not finite, so therefore R is not a group. So 0 belongs to R, but inverse of 0 does not exist. Therefore, now how to convert a set of all real numbers to be a group, or under what condition set of all real numbers will become a group under the operation multiplication. So that is so we have the difficulty only when x is or even a equal to 0, that is inverse of 0 does not exist. So there is only one element, that is 0, for which inverse does not exist. So therefore, so inverse for the remaining elements exist. Therefore we remove 0 from this set, so that we denote by r star. So r star, the meaning is r minus singleton 0. So now we consider this r star under the operation multiplication. So this will be a group, that is some product of any two. So first one, closure property. Product of any two non-zero real numbers is also a non-zero real number. So therefore the closure property is satisfied, and so the associative will be true. A dot b dot c equal to a dot b dot c. And what about the identity element? The identity property is a dot e equal to e dot a equal to a. So here identity element is equal to 1. So this belongs to R. Therefore identity element exists in R. The fourth one, A dot B equal to B dot A equal to E, that is A dot B equal to B dot A equal to 1. Now A into B equal to 1, B equal to 1 by A belongs to R, whereas this A will be non-zero because of the construction of R star. So this belongs to R star. Therefore inverse, so this we call as multiplicity inverse. Inverse of A is 1 by A. Therefore R star comma dot is a group. Similarly, Q star comma dot is a group. So the operation is defined already here. So these are some of the examples in which we have the operation as multiplication. So we can take the matrices also. So set of all matrices will also form a group. So another set of examples. Set of all 2 by 2 matrices with integer entries is a group under matrix addition. Under matrix addition, the set of all 2 by 2 matrices will be a group. So if we add any 2 by 2 matrix, so the result will be a 2 by 2 matrix. Therefore closure property is satisfied, and matrix addition is always associative. And what about the identity element? Here identity element is 0 0 0 0. So this identity we called as additive identity because identity with respect to the operation addition. And inverse of A, B, C, D. So what is inverse of A, B, C, D? So this one is minus A, minus B, minus C, minus D. So this we note as integer entries M2 by 2 of Z. Set of all 2 by 2 matrices with integer entries. So here you will see the set. What is M2 by 2 of Z? So this is equal to set of all A, B, C, D such that A, B, C, D belongs to Z. So in a second you can consider the same M2 by 2 of Q. So this will be group under matrix addition, and M2 by 2 of R, M2 by 2 of C, and you can take the rectangular matrices also. So M3 by 2 of Z. That is, we can take it as M n by m of some, you can take this some other variable, or we can write directly Z n by m of q, so etc. So this will be the group under matrix addition. Okay, so with this we will end this video. So in the next video we will see the properties of group and
some more examples. Okay, thank you.